A double bond in chemistry is a chemical bond between two chemical elements involving 4 bonding electrons instead of the usual 2. The most common double bond, that is between 2 carbon atoms, can be found in alkanes. Many types of double bonds exist between 2 different elements. For example, in a carbonyl group with a carbon atom and an oxygen atom. Other common double bonds are found in azo compounds, imines and sulfoxides. In skeletal formula, the double bond is drawn as 2 parallel lines between the 2 connected atoms. Typographically, the equals sign is used for this. Double bonds were first introduced in chemical notation by prominent Russian chemist Alexander Butlerov. Double bonds involving carbon are stronger than single bonds and are also shorter. The bond order is 2. Double bonds are also electron-rich, which makes them reactive. Double bonds in alkanes. The type of bonding can be explained in terms of orbital hybridization. In ethylene, each carbon atom has 3 sp2 orbitals and 1 p orbital. The 3 sp2 orbitals lie in a plane with 120° angles. The p orbital is perpendicular to this plane. When the carbon atoms approach each other, 2 of the sp2 orbitals overlap to form a sigma bond. At the same time, the 2 p orbitals approach and together they form a pi bond. For maximum overlap, the p orbitals have to remain parallel, and, therefore, rotation around the central bond is not possible. This property gives rise to side transisomerism. Double bonds are shorter than single bonds because p orbital overlap is maximized. With 133 pm, the C=C bond length is shorter than the Ca-C length in ethane with 154 pm. The double bond is also stronger, 636 versus 368 kilojoules per mole, but not twice as much as the pi bond is weaker than the sigma bond due to less effective pi overlap. In an alternative representation, the double bond results from 2 overlapping sp3 orbitals as an abent bond. Types of double bonds between atoms. Variations, in molecules, with alternating double bonds and single bonds, p orbital overlap can exist over multiple atoms in a chain, giving rise to a conjugated system. Conjugation can be found in systems such as dienes and enuns. In cyclic molecules, conjugation can lead to aromaticity. In cumulines, 2 double bonds are adjacent. Double bonds are common for period 2 elements carbon, nitrogen, and oxygen, and less common with elements of higher periods. Metals too, can engage in multiple bonding in a metal ligand multiple bond. Group 14 alkane homologues, double bonded compounds, alkane homologues, R2E=E2 are now known for all of the heavier group 14 elements. Unlike the alkanes, these compounds are not planar but adopt twisted and or trans-bent structures. These effects become more pronounced for the heavier elements. The distonin 2CHSN=SNCH, CMe3, 2 has a tin-tin bond length just a little shorter than a single bond, a trans-bent structure with pyramidal coordination at each tin atom, and readily dissociates in solution to form 2CHSN. The bonding comprises 2 weak donor-acceptor bonds, the lone pair on each tin atom overlapping with the empty p orbital on the other. In contrast, in disolines each silicon atom has planar coordination but the substituents are twisted so that the molecule as a whole is not planar. In diplumbans the Pb=Pb bond length can be longer than that of many corresponding single bonds. Plumbans and stanins generally dissociate in solution into monomers with bond enthalpies that are just a fraction of the corresponding single bonds. Some double bonds plumbans and stanins are similar in strength to hydrogen bonds. The Carter-Goddard-Malraux-Trinquier model can be used to predict the nature of the bonding. References. Picker paragraph, Pecker. Riddle, Sebastian. Patschk, Michael. Triple bond covalent radii. Chemistry, a European Journal 11, 3511 Euro 20 doi, 10.1002/Chem 200,401,299. PMID 15,832,398.